I can show you a small experiment. Okay, so we talked about this photo or the discharge tube, right? So the discharge tube, we talked about something like this. So this was connected to the negative, this was connected to the positive, and when you expose some radiation, right? So we said the electrons were coming here and then completing the circuit, showing some current in the galvanometer, right? So I don't have a discharge tube, but there is something called photodiode, which is very similar to photoemissive cell. So take it down. There is something called photocell or photoemissive cell. So what it does is it looks something like this. You see this? It looks something like a LED, right? But inside this, they may have something, again, it's not exactly a photoemissive cell, but it's something similar. We'll talk about that later. But the photoemissive cell looks something like this. And inside that you have a plate like this, which we will be connecting it to the negative. And then there will be a axial thing called anode. So this is called cathode. This is anode, right? And if I had a galvanometer here, I'll be seeing the reflection. So sometimes this is referred as emitter, and this is referred as collector. So when it is exposed to light or UV rays or infrared rays or something like that, right? Radiation. When I say radiation, we mean everything, right? It can be anything. UV rays, IR, radio waves, anything. So when this falls on it, right? So it will be emitting some electrons. So this will be collected by the anode. So that's why this is called emitter and this is called collector. Okay. So this is minus and this is plus. But if I don't have the UV rays, what will happen? Will you see any deflection? No, right? Only when you put some kind of radiation, you will be able to see the galvanometer reflection. Okay, so let's try that. So I can show you again, as I said, this is not a photoemissive cell. Maybe I will try to find out if there is some photoemissive cell available in the market. But this is actually photodiode, but the functioning is slightly similar. The applications are also very similar. So what I have done here is, so it's very similar to this. I take a photodiode here, and then it's connected to the battery, and then in between I have a galvanometer. Okay. So right now, even with this light, right, it is supposed to show some kind of a current, for which I have a microammeter. So this is supposed to be like 100 microammeter or microamps, right? So it's very, very sensitive. So even a very small current can be detected with this. Okay. So right now in the galvanometer, I don't know if I can convince you from there. So if you really see this, right, if I cover this, it's making a very small movement. Maybe you are not able to see it, maybe you can see it, right? If I cover this, the light is not falling on it, but when I remove this, it's very, very minute, right? Just half this thing, you cannot see it. But if I connect it to this one, right, so probably you can see it better. But another problem I have is, this is supposed to be kept like this, which means you will not be able to see anything. Let me keep it like this. Let's see if it's going to work still. So this goes to the plus. You see that? So again, it's supposed to be at 0, but then since you folks have to see it. So if I make it lie down on the table, it will be 0 there. But the actual reading doesn't matter for us. So I want you to see that, when I connect this, you can see there is some deflection. So if I close this, you see that it's decreasing, right? The moment I open this, you can see it's increasing, right? So that means whenever the light is falling, right? So there is some kind of a electrons going here and then completing the circuit, right? But then this visible light is going to be a little bit less, and I have this infrared lamp here, which is kind of very powerful. Meaning, when I say powerful, is it high frequency or high intensity? High intensity, right? Not frequency, because infrared is, infra means inferior, ultra means higher. So what is that? Ultraviolet means higher frequency, infrared means lower frequency, right? So this is actually lower frequency, but the intensity is high. So just observe what's happening. So you see that? So in fact, it's not able to take this because it can measure only up to 100 microamps. So even if I connect it to this galvanometer, I am going to see the same thing. So the moment I switch it on, you can see this thing is going pretty high, right? So that shows that the current is actually high when you connect it to a very high source or powerful source. So basically, the intensity is very high in this case. And that's what we saw in the first this thing, right? When the intensity is higher, the current is also high. Okay, that makes sense. Again, as I told you, I'm kind of cheating here because it's not really a photoemissive cell. It's actually a photodiode. It's slightly different. But for your understanding, for now, it's good. I hope you understood what we talked about here. And because this we'll be studying again in semiconductor devices later, right? So there are a lot of electronic devices which we need to study. Okay. So I hope you have some idea about that one. So can I erase this one? Or still anybody still copying this? Or copying? Okay. So as I said, there are some situations where light behave like particles, and there are some situations where light behave like waves, right? So there were always some confusion going on between the scientists whether to take the wave nature or the particle nature. So there was one scientist called Lois de Broglie. He was a French scientist. Lois de Broglie. People are studying French. Is that the correct pronunciation? De Broglie, is that correct or some other pronunciation? I think it is somebody's in your book. I think it is given as De Broglie. Is it supposed to be pronounced like that? De Broglie? Don't know. Okay. So I think it's something like a silent letter here. So De Broglie or something is the correct pronunciation. It doesn't matter. De Broglie. So he said that there was no real reason to accept particle theory or wave theory. So he said, why should we, fight between us saying that, okay, it has to be a wave or it has to be a particle. Why can't it be both? And that's when the dual nature started gaining acceptance. So there was no real reason to accept particle theory or wave theory. Exclusively. Both were correct. Radiation. So whenever we say radiation, we mean the electromagnetic spectrum. EM waves. So light is also part of this. So electron radiation must be regarded as a physical characteristics. Must be regarded as a physical characteristic with dual nature. Okay, so that's an important quote what de Broglie said. There was no real reason to accept particle theory or wave theory exclusively. Both were correct. Radiation must be regarded as a physical characteristic with dual nature. And he didn't stop there. He also said a very important question he raised was, if a wave can behave as particle, right? Why can't particle behave as wave? That was the main question he put forward. So, if radiation can behave as wave and matter, why can't matter behave as waves? And the only support which he had was, he said that in nature most of things are symmetric. So everything is kind of symmetric. So when wave can behave as matter, why can't matter behave as waves, right? What do you mean by wave and what do you mean by matter? What are the two important things? Like, what is so different about wave and what is different in matter? What do you mean by matter? It has got mass. Wave does not have any mass. So this is more like energy. This is mass. So that's the important thing.